Our next session is fossil-based energy systems. We're a little bit behind on time, so we're going to go straight into the talks. We've got three really interesting talks, one about ionic liquids, which is really important in terms of making materials that can do very good separations, very efficient separations in terms of CO2. We have a talk that will fold economics as well as technology into it, which is a critical piece, because if it's not economic, it's never going to happen. And then we have a talk which is kind of special in terms of the combination of coal to electricity and generating hydrogen in a separated fashion altogether, which is sort of a special thing since coal is this vast resource that's very hard to use, and hydrogen is something which is carbon-free, but it's pretty hard to make without having carbon show up in some other place. So we have some neat opportunities in terms of the programs, but other than that, I'm not going to say more. So if Edward could head up, we'll get going on this. Our first speaker is Edward Maginn from Chemical and Biomolecular Engineering at University of Notre Dame. He joined the faculty in Notre Dame in '95 and currently holds the Dorini Family Chair of Energy Studies. He's also the chair of the Department of Chemical and Biomolecular Engineering. Edward.
Thanks very much. It's really a great pleasure for me to be here to tell you about some of the work that our group has been doing on looking at ionic liquids for CO2 capture and separations. And so I'm here to report the results of our team. I show you a picture here of some of the faculty and students involved in this effort. And I think we don't need to explain why CO2 capture is important. I think yesterday's sessions really made this abundantly clear that we have to think about carbon capture if we're going to be able to meet some of the sustainability and CO2 targets that we all need. And the typical way that people think about this is in terms of thinking about coal. And certainly CO2 capture is important for coal. Coal is a huge available resource. There's a lot of coal reserves and installed base of coal-fired power plants. And we know that fossil fuels contribute or make up about 85% of our base energy load. But I'd like you to think about CO2 capture in other aspects as well. We know about shale gas is also now becoming a very important element for our energy mix. And although natural gas has a lot less carbon intensity than coal does, we still have carbon emissions. So we replace gas-fired power generation for the dirty old coal-fired power generation, but we still produce CO2. And so you could think about needing to do capture of CO2 from these situations. The flue gas and effluent is a little bit different from coal-fired power plants. And then I really like Thomas's talk yesterday. I borrowed his image of this about the reduction of CO2 to make fuels or to make chemicals. And the obvious question here is, where's this CO2 going to come from? You're going to have to do a separation if you want to be able to do CO2 reduction as well. And the other thing to think about is, if you want to do CO2 reduction catalytically, how are you going to get the CO2 into solution? And I want to show you some work on ionic liquids that may be a very good liquid solvent that can generate very high concentrations of CO2 to be used in catalysis. And then lastly, we heard yesterday about negative CO2 emissions, this notion of being able to use biomass and then in the production of energy from biomass to still capture the CO2 in order to have a net negative CO2 emission. So in all of these cases, we're talking about having to separate CO2 from some effluent stream. And they have very different conditions, very different temperatures and pressures. So what we need is a very versatile platform on which to be able to think about doing CO2 separations. Now, we just heard in the previous talk, Professor Bao talking about the typical way of doing this is with amines. And you can think about really post and pre-combustion as two examples at different ends of the spectrum of our CO2 capture problem. In the top slide there, you can see that what we have is kind of a typical post-combustion scenario where you take some carbon source and combust this in air. That generates a flue gas that's comprised of carbon dioxide, nitrogen, water, and some other things. And we need to do the separation to remove the CO2 from that. It's important to recognize that the flue gas there is at relatively low temperatures and pressures, maybe 40 to 50 degrees C, maybe about 1 bar. And the partial pressure of CO2 is actually about 1/10 of a bar. This becomes a pretty challenging separation to conduct. Moreover, if you want to do sequestration, you have to raise that pressure of CO2 up to about 150 bar in order to sequester this. So that's part of the energy cost of this whole carbon capture process. On the other hand, if you think about something like a gasification or a pre-combustion application, here we gasify the carbon. It could be from biomass, it can be from coal. We can then do a water-gas shift reaction, and then the primary system that we have to do a separation on is a high temperature and high pressure mixture of mostly CO2 and hydrogen. So now we're up to maybe 200 degrees C, 60 bar. It's a very different type of separation than we have to do from the post-combustion aspect. So, and there's really a range of different separations we could think about. If you do combustion of natural gas, very different conditions there. So what we'd like to have is a platform that can allow us to think about doing these type of CO2 separations for a range of things. We favor using solvent-based methods. This is a simple little movie kind of showing how this works. If you have a flue gas containing CO2 and, say, nitrogen or maybe hydrogen, you'd like to bring it into contact with a solvent, shown here as these yellow molecules, that preferentially will associate with the CO2. The other gas is left to either process or you can vent to the atmosphere. And then the complex solvent, which carries the CO2 with it, is then regenerated with some trigger. It could be heat, it could be other things like a photo effect or something. Then you can recycle the solvent and you've done the separation. So this is the basic idea behind a liquid-based separation of a gas. And this is a very well-established technology. This is one of the reasons why we like liquids. Gas processing with liquid contactors is well known in chemical engineering. The trick here is we need a solvent that can operate under these different conditions that we require. So some of those properties that we need are a high selectivity and affinity for the carbon dioxide. We'd like for these things to be what I would call tunable. That means they need to be amenable for use in either the pre or post combustion. Very different temperature, pressure conditions can separate CO2 from either hydrogen or from nitrogen. And so we want to have the ability to kind of adjust the properties of this solvent to meet these different needs. Obviously, you want this to be a thermally stable solvent because we want to be able to regenerate this and have a long lifetime. It can't be a one-shot type of a solvent. And especially in a pre-combustion application where the temperatures are high, we need to have very low volatility. If you're losing this continuously to evaporation, or if you have to add extra processing to recover your solvent because it's volatile, this is really a very expensive proposition. So in the end, what our goal here is to try to optimize solvent properties in order to minimize the regeneration costs. We don't want to have to pay a huge energy penalty in order to recycle the solvent. But we also want to minimize the liquid flow rates so that the size of the equipment is smaller to reduce capital costs. And that's a kind of often in tension between the regeneration energy and the capital costs. So as has been mentioned, the conventional technology for doing CO2 capture right now is aqueous amines. Just giving you an example of one type of an amine, a monoethanol amine or MEA. The idea here is that at low temperature you contact MEA, which is dissolved in water. It's about 70% water. And it takes two MEA molecules to react with each CO2 molecule, forming a carbamate and an ammonium species. Further, you can react with water to form bicarbonate. This reaction can be reversed by heating this up, and you can recover the CO2 again. So this is proven technology. It's been around for a very long time, and it works, but it has several drawbacks that really limit its application in the type of systems that we would like to apply it to. For one, the amines are volatile. They smell very bad. If you think about putting these in a power plant, you're going to have extra processing to capture the amines because you don't want to emit these to the atmosphere. I mean, you're also thinking about air pollution problems of taking CO2 out of the air and releasing amines into the atmosphere. That's not a very good trade-off. They tend to be very corrosive, so materials of construction are important. And probably the biggest problem with amines is that because you have all this water you're carrying around and having to vaporize during the regeneration process, they have a very large energy penalty, upwards of 25, sometimes estimates are even 30% of the output power of the power plant is going to be used just to run the gas separation process. So the parasitic energy load of this is much higher than thermodynamics says should be possible. And so our goal is really, can we develop liquid solvents that can overcome some of these problems with conventional amines? And so We've been, for some years now, working on a class of liquids called ionic liquids, which have been around for about, this type of ionic liquids has been known for about 20 years now. And they're just simply salts that are liquid under ambient temperatures. So if you look at this picture up in the upper right, this is one of our graduate students holding a little vial of an ionic liquid, and it's not 800 degrees Celsius. You can hold it in your hand. But that's a pure salt. It's not dissolved in water. It's not dissolved in a solvent. It's 100% salt, but it happens to be liquid at room temperature. And there's a huge chemical diversity of compounds that can be made into ionic liquids, which really makes them intriguing platforms for thinking about gas separations. Because they're salts, they have a very high cohesive energy density. They're essentially non-volatile liquids. You can put this under a ultra-high vacuum and it'll just sit there and won't do anything. You can see here, this picture here, this is an image of an ionic liquid with CO2 dissolved in it where we're pulling a vacuum. The CO2 just bubbles out of the liquid and the liquid stays behind. So the removal of CO2 from the ionic liquid is trivial, and that makes them very attractive. They tend to be non-corrosive. We don't have to use water. We can use these in an anhydrous manner, so we don't have to carry around the excess water baggage. And this plot here shows that they actually have an intrinsically high physical selectivity and solubility for CO2. This is a plot from my colleague Joan Brennicke's experimental work showing you the mole fraction of the gas versus pressure at one temperature. The red symbols are CO2, and you can see oxygen and nitrogen are down here with very, very low solubilities. So already you have a solvent that, this is sort of a stock pyridinium-based bistriphylamide, which has a very high selectivity for CO2. The other thing that's important, and I'll come to this in a bit, is we can design these to even chemically react with CO2 to get even higher selectivities. So our approach in the GSEP project has been to follow this, what we call model-guided discovery. And Ed Rubin, I think the next speaker, is going to talk a little bit about how you do process modeling to try to understand the economics of CO2 capture. We think it's very important to start with process modeling, understand the nature of the process, and what are the properties of your solvent that are most important that are driving the costs. Mark Stadtherr at Notre Dame is doing some of that work for us, and then he tells the computational group here, here are some of the properties that we need out of our ionic liquid. Things like capacities, binding energies, heat capacities, those kind of things. And my group and Bill Schneider's group then try to predict with atomistic simulations what particular molecules should have those favorable properties. Brandon Ashfield in chemistry will then make those molecules, and Joan Brennicke has the capability to measure the thermodynamic properties, gas separations, and all the different properties as well. And then through an iterative process, we try to optimize these things so that we're not just kind of randomly synthesizing molecules and throwing them into the lab, but we have some intelligent design involved in, I guess intelligent design is, that's not the word I was looking for. We have a good idea of what we're trying to make here. So let me tell you a little bit about some of the computational methods that we use. We like to be able to predict isotherms of CO2 and other gases in the ionic liquid from first principles. And to do that, we use atomistic Monte Carlo simulations. The basic idea here is we have a liquid phase shown here in the upper left, coupled thermodynamically, although not physically, to a gas phase. And we use a series of stochastic Monte Carlo moves to satisfy the phase equilibrium condition. And we can do that for a given set of temperatures and pressures, and then we get a single point on an isotherm. Typically, that means we have to simulate hundreds of these ionic liquid molecules in 4 to 5 nanometer periodic systems. These are now fairly standard kind of calculations that you can do a matter of days to get a full isotherm. So we can start from drawing a molecule on the computer to getting an isotherm in really less time than it takes to synthesize and measure it experimentally. And we can do this in parallel fashion on lots and lots of these at one time. So we now have a capability of doing rapid screening of ionic liquids for their uptake properties. And this just gives you an example of some of the things we can do. I'm showing you here 2 different ionic liquids. On the left is something called butyl-methyl-imidazolium bistriphylamide. The cation here is a butyl-methyl-imidazolium. On the right is a very similar ionic liquid, it's just that there's a hexyl chain instead of a butyl chain. These 2 were chosen because there's an awful lot of experimental data on CO2 uptake in these ionic liquids, and we wanted to benchmark our calculations against that. So here we're plotting pressure as a function of mole fraction of CO2 at different temperatures. And there's a lot of information on here. Bottom line here is that the simulations are quantitatively capturing the experimental isotherms And we're not fitting to the experiments. These are purely predictive calculations. One of the most important quantities for us to get right is the enthalpy of absorption. And for physically dissolving CO2, that ends up being between 12 and 16 kilojoules per mole experimentally, and the simulations are able to capture that quantitatively. We can also do hydrogen. So if you're thinking about pre-combustion applications, we'd like to understand hydrogen solubility as well. Hydrogen is much less soluble in the ionic liquid than CO2. Here there's also less experimental data. It's a very hard measurement to make, but there is some. And so again, for the same two ionic liquids I showed on the previous slide, you can see different isotherms. And the simulations here are now at different temperatures. Interestingly enough, these lines correspond to different experimental sets of data. There are 4, 3 of which agree with one another and 1 which doesn't, 1 which predicts hydrogen is much more soluble. Our simulations agree with the other 3 sets of experimental data. So in some sense, the simulations are helping us provide a check on the consistency of literature data that maybe doesn't always agree with each other. The other thing that's interesting to me anyway is that the calculated and experimental enthalpy of absorption is actually positive for hydrogen in an ionic liquid. If you think about a free energy argument, that means that entropy is what's really responsible for the solubility of hydrogen in the ionic liquid. And this is typical of very low solubility gases. What that means is that unlike CO2, if you heat the liquid up, the solubility actually increases. And we're able to capture that positive enthalpy in our simulations, and it's been observed also in the experiments. So what you'd really like to do now is be able to do the selectivity calculation. We don't want to just think about pure CO2 or pure hydrogen. So we've done that, and this table has a lot of numbers. I don't expect for you to look at these and see that. I just would like to point out one thing about this is for these 2 different ionic liquids, the selectivities that we compute are on the order of, say, 45 to 50 for CO2 over nitrogen. And this is based on just physical dissolution of the CO2 and nitrogen into the ionic liquid. We can calculate an ideal selectivity by just fitting the pure isotherms to a simple model and assuming that these things don't interact with each other. And that actually gives us very good agreement with our computed selectivities. An important thing to point out, however, is that if I just made the approximation, which is often done in the literature, the experimental literature, that the ratio of the Henry's law constants gives me the selectivity, I would greatly overestimate the selectivity. You would estimate that it's on the order of 70, when in fact the selectivity is more like 50. And this is really, I think, one of the benefits of these models is that you can test these type of predictions because mixture experiments are much more difficult to conduct than the pure gas experiments. And so we didn't really have good information about this. So let me move on and talk a little bit about increasing the capacity of the ionic liquid for CO2. These physical solvents I've been talking about previously are very good if you have high pressures and low temperatures. But in cases where that's not the situation, the capacity of these liquids is going to be too low. So you'd like to add reactive groups in order to increase the capacity. And I just show you here an experimental plot again of mole fraction of CO2 versus pressure for a physically dissolving ionic liquid. This is the one I was showing you on the previous slides. And what you can see here is that you have to go up to very high pressures, 10 bar, to get a mole fraction of about 0.3 for CO2. But that's occurring at 10 degrees C. As the temperature increases, that capacity drops dramatically. And if you're operating around a tenth of a bar like you might in a post-combustion capture application, you really aren't dissolving any CO2 at all. So you need to add chemical reactivity to increase the capacity. And the obvious question is, how strong should you bind? If you bind very strongly, you're going to have to pay a larger energy price to remove the CO2 and regenerate the solvent. So we'd like to try to maximize the capacity. Calculations done by Bill Schneider has helped us figure out how to do this. What he did is he looked at the relative free energies, or reaction energies, for CO2 binding on a conventional monoethanolamine. And he based this as a zero energy reference state. So what he did is he added CO2 to MEA, and the first CO2 bound, and he called that a zero reference energy. And then he went ahead and did the deprotonation reaction to form the carbamate and the ammonium species and calculated that energy and set that as a reference. So what we call this first step, when you can halt the binding of CO2 after the first case, is a 1-to-1 binding. 1 amine for 1 CO2. The 2-to-1 binding, though, involves a deprotonation reaction, and it takes 2 amines for 1 CO2. And we know that this is the mechanism that's operational for MEA. So then Bill did a calculation where he added an amine group onto a cation of an ionic liquid, a pyridinium, and he found that relative to MEA, the first binding event is slightly uphill, and the second binding event is very negative, minus 71 kilojoules per mole for the deprotonation. So the prediction is that if you put an amine group on a cation, you'll see the same 2-to-1 binding that you see with conventional aqueous amines. Surprisingly, however, if you put the reactive group on the anion, in this case an amino acetate anion, it's downhill for the first binding event, but then it's a big uphill, 71 kilojoules per mole, to do the deprotonation reaction. So you can arrest the reaction here at this first step if you put the reactive group on the anion. And this basically doubles the capacity of CO2 in the ionic liquid if you put the reactive group on the anion and not the cation. And this is unique to ionic liquids, and so that's what we've done. We've also built a little model that's a very simple single-site Langmuir type model that says, all right, we're going to bind to CO2, one CO2 to one anion. If you can compute basically the free energy, you can calculate the equilibrium constant, you can get the isotherm, basic thermodynamics. We estimate the free energy by just calculating the translational entropy of CO2 in the gas phase and saying that that's what delta S is for this reaction. And then we compute the bond strength delta H. So for different delta H's, you can get different characteristic isotherms. Here is what the model would predict for 50 kilojoules per mole binding. At low temperature, you get almost 1-to-1 binding, and then as you raise the temperature, the binding decreases. So the idea here would be you could capture CO2 at low temperature and low pressure, and desorb CO2 at high pressure and high temperature. And that would be, the delta there is the capacity of your solvent. So we've shown that this works. You can add reactive groups onto anions. Here's 2 different amino acid-based anions. And the experiments show that we do get this 1-to-1 binding. And the uptake isotherms are really consistent with the first principles predictions. And we've confirmed the mechanism here with calorimetry and vibrational spectroscopy. And we think we understand the chemistry of these systems really well. So this really led us to develop this kind of class of ionic liquids having aprotic heterocyclic anions. These are examples, pyrrolide, imidazolide, and pyrazolide, that can do this 1-to-1 binding, and we can tune the binding strength by changing the R group functionality along the ring. So here's an example. If you take something like a pyrrolide, there's a reactive group here at this nitrogen center, and if you just have basic pyrrolide, CO2 will react and bind quite strongly, 110 kilojoules per mole. This is the prediction. You can add electron withdrawing groups around the ring. So in this case, a cyano group at the 3 position, the binding goes down to minus 70. If you put a little bit closer to the nitrogen group, now at the 2 position, you're down to about minus 50 kilojoules per mole. And so our process simulations tell us that minus 50 kilojoules per mole is a sweet spot for some of the applications. So we went ahead and made this 2-cyanopyrrolide system. And sure enough, experimentally, we see exactly what we would have predicted from the models. We see this kind of Langmuir type isotherm. So this is now experimental data. And then as you raise the temperature, the capacity goes down. Experimentally, we're about minus 43 kilojoules per mole. So the calculations predicted minus 49. This is pretty reasonable agreement with the experiments. And I didn't talk much about this, but we can also show that the viscosity of these things doesn't change when you react with CO2, which is different from amines. The viscosity of amines goes up considerably when you dissolve them in CO2. So over the course of this project, we've made a whole bunch of these different ionic liquids. And here are all experimental isotherms for a bunch of different anions with one particular phosphonium cation. And so you can see from indazolide, which has the highest binding of minus 54, we get very rapid saturation at low pressures. Whereas if you go down to 1,2,4-triazolide or 1,2,3-triazolide, these have lower binding energies of, say, minus 37, minus 40, and the isotherms are much flatter here. So we can kind of dial in the binding energy depending on what we want based on these kind of calculations. Now, I should tell you that maybe the simulations aren't perfect. What we found was that we're not able to quantitatively predict all of the isotherms perfectly well. We're using a very simple model. We have a gas phase anion, and we're just calculating the delta H of reaction of a CO2 reacting in the gas phase. What we observed experimentally is some different isotherms here for 4 different ionic liquids. And the observation is that this is a pyrazolide anion, should bind the strongest, followed by this 2-cyanopyrrolide, and then a 1,2,4-triazolide. And 1,2,3-triazolide should not bind very strongly at all. Unfortunately, the calculations didn't catch that trend. We did see that the pyrazolide should be the strongest binder, but we missed the fact that 1,2,3-triazolide doesn't bind as strongly as the other ones. So in this case, our simple model was breaking down, and what we realized we had to do was add more reality into the model. So what we did is we did first principles ab initio molecular dynamics simulation of the cation-anion pair in the gas phase. So this is showing that the anion interacts very strongly with the cation, as you might imagine. And this has a profound effect on the reaction chemistry. And I won't go into the details of this other than to kind of cut to the chase and show you the result here. Here's an example of this would be 1,3,4-triazolide with a CO2 bound to it interacting with a particular cation. And what you can see here is that the bond length here between the CO2 and the anion depends upon the interactions that the anion is having with the cation. And this in turn affects the binding energy. The plots on the left show you different distributions during the course of the simulation of the distance between the CO2 molecule and the anion and the cation. And what you can see is it's very dynamic, and the energetics change because of the interactions between the anion and the cation. If we put that added realism into the model, what we can find is that we do get the proper order of the adsorption now by using this ion pair model. So this gives us a better result. Just real quickly now, we also have been able to try to simulate the reaction in the formal condensed phase, not just an ion pair in the gas phase. And Quentin Sheridan has poster 30 last night where he showed how this works. We can construct a thermodynamic cycle, basically, and calculate solvation free energies and coupling that with the gas phase free energies to get condensed phase free energies. The last thing I'll mention is that we're working on coming up with cooperative binding models where we can get beyond the sort of Langmuir model. The Langmuir model is nice, except you have a sort of delta pressure or delta temperature that sets your given capacity. What nature has done is use cooperative binding, for example, in hemoglobin, where you can get sigmoidal type isotherms. So you have multiple binding where the first binding event makes the second binding event more favorable. That leads to this sigmoidal type isotherm, and now you need much smaller either pressure differences or temperature differences to get a given capacity. So we've made a whole bunch of different ionic liquids with 2-to-1 uptakes that we hope will have this type of cooperative binding event. And very recently we measured some of the isotherms for these, and for this particular system we do start to see upwards of 2 molecules of CO2 binding for each ionic liquid, and evidence, although not quite perfect, of some sigmoidal shape in this isotherm. So we're pretty excited about that. So just to quickly summarize, we've designed ionic liquids that have both high CO2 capacity and can be tuned over a wide range of energies to make them suitable for different types of CO2 separations. And what we're working on are improving the computational methods that can help us choose other ionic liquids and looking at cooperative binding events. So finally, I just want to acknowledge, very grateful for the support of GSEP that's allowed our team to come together. And here's some pictures of my co-PIs. Brandon Ashfeld did all the synthesis. Joan Brennicke did the thermodynamic property measurement. Bill Schneider, the quantum chemical calculations, and Mark Stott here, the process modeling. And thanks very much for this opportunity to present our work.
Okay, we have about 3 minutes for questions.
So what's the stability of the ionic liquids in the presence of water, and especially water at high temperatures, and then also SOx and NOx?
Great question. So for water, some of the ionic liquids we find will reprotonate. The anions will reprotonate in the presence of water. The ones that I was showing you here don't do that. The cyanopyrrolite in particular, the one where we've done most of our work, we've done very extensive tests with water. In fact, all of them are stable in the presence of water. The problem is the presence of water and CO2 because the acidic environment can deactivate them. So the answer is some are stable, some are not stable, and we're trying to understand that. SOx and NOx will react with the reactive amines, and very hard to get them back off once they react. So in any kind of an application, if you have a lot of sulfur, you'd have to have a desulfurization step before you would want to do the CO2 capture. That's kind of our current thinking on that.
What kind of pressures are necessary to get the CO2 to desorb?
So Typical, if you look at the isotherms that we have there, we want to desorb them at as high a pressure as possible because then we have to take this up to pipeline pressures. We can desorb these things at around 140 degrees C. The ionic liquids are still stable. And the pressures then are a few bar at that point, and you can get good capacity. We don't want to go to vacuum at all. The economics of vacuum for these systems is not good. So we want to absorb them at always above atmospheric pressure and desorb them at higher pressures and just use temperature as the driver. But in principle, you could use vacuum and do this at lower temperatures. It just turns out that for this particular system, it looks like the economics are better if you use higher temperatures and higher pressures. That's assuming, of course, that you have to compress the CO2 back up to pipeline pressures.
Okay, one last quick one.
I've heard that ionic liquids are very difficult to manufacture and worth more than their weight in gold. So do you envision that these may have some of those same cost challenges?
Yeah, that's always an issue with, these are new molecules. Many of them have never been made before. So they are worth their weight in gold when Brandon is making, milligram quantities of them with his very talented graduate students. The idea, though, is that these are not particularly exotic materials. They're carbon, hydrogen, nitrogen. And so that if you were to make these on scale, the cost will go down. I'll tell you that Petronas, the Malaysian oil company, has just installed a process where they're doing mercury removal with ionic liquids, and they're using ton quantities of ionic liquids in that process. The ionic liquids have been stable for a couple years, and so there are examples of large-scale industrial uses of ionic liquids, and really what you need is those kind of applications where you can make these on scale to get the cost of the liquid down. But we're very cognizant of that when we're designing these things. We're trying to avoid any kind of exotic materials that will really drive the cost up.
Great. Thanks again, Edward.